Hello, we have learned how to work with the joint distribution of two random variables x and y. So fx of x and y, so the PDF or CDF. And we know that this is related to joint CDF, fx of x and y, and it represents the distribution of the density of probability at different locations. In this video, we will learn alternative methods to work with this distribution, which is joint characteristic function. So we want to find another alternative way to learn with these guys. We can take, for instance, Fourier Transform or Laplace Transform. So what we learned from your other courses, we want to see if we can use them in random variables or not. So particularly, we want to define a joint characteristic function of a random variable. So the joint characteristic function is basically the 2D Fourier transform of the joint PDF fxy of x and y, but with some minor difference. So again, in this video, we learn how to use the joint characteristic function as an alternative for the distribution. Then we will learn about joint moment generating function as another alternative. This is basically similar to a Laplace transform with some minor difference. If you consider a pair of random variable, we can define e to the power of g x omega 1 and then plus y omega 2. So basically this portion is a linear combination of the pair of random variables x and y, and this is an exponential function of that. So you define this one. So this is a function of pair of x and y. So this is like g of x and y, okay? So if you take a mean of that, this is going to be a moment of your distribution. So mean of that is a moment of your joint distribution. In other words, the joint characteristic function is a moment of your random variable. So is expected value of this function. Now let's see. The expected value is the value that this function can take. So this is this one. And then you do integration over both variables x and y from minus infinity to plus infinity. And then you multiply it by the joint PDF. Now, let's forget about these moment things and so on. Now, compare this one with the Fourier transform. So if you have a function of, let's say, f of x, and you want to get its Fourier transform, you multiply by e to the power minus j omega x, and then you integrate it with respect to x from minus infinity to plus infinity of dx. So this is called f of omega, is Fourier transform. So there is a difference between Fourier transform and this expression. Now, if you had a function with two variables, instead of f of x, we had f of x and y, and we wanted to do 2D Fourier transform, we would have had minus omega 1x and then omega 2y. Of course, this is plus and j here. So in that case, you would have done another integration with respect to y and integral with respect to y minus infinity to plus infinity. And then this would be a function of f of omega 1 and omega 2. So basically this is Fourier transform. The only difference is that here you have a minus, here you don't have. So basically I could say that this is a Fourier transform, 2D Fourier transform of the PDF, the joint PDF of f of x and y of x and y. But after you take a Fourier transform, you have to replace omega 1 by minus omega 1 and omega 2 by minus omega 2. So basically it is Fourier transform, but with some minor differences. So now let's Forget about these minor things. The truth is that these minuses, mathematically, it would have been better to had it there, but statisticians, they started to use these characteristic function about the same time that the literature of Fourier transform was developed. So in one community, they put these minus, in the other one, which is statistics, they didn't. And once you establish enough literature, it's hard to go back and erase all those books and so on. So we are stick with this definition. So this is defined, and because of Fourier transform, there is a one-to-one relationship. So if you have the joint characteristic function, you can get your fx y of x and y using back from the characteristic function fx of y of omega 1 and omega 2 using some double integrals that you know, so you can get it back. And basically this inverse transformation is also similar expression. Another point I wanted to make is that basically when you calculate mean of, let's say, any function g of x and y, this is a double integral of g of x and y and a joint PDF fx of y and fx and y. Yes. So basically this is the dot product of g, x and y and the PDF. And here you have the dot. So basically this is the inverse Fourier transform of the joint PDF, and the other one is there. So the inverse of this transformation is given by this expression. So it means that there is a one-to-one relationship. So there is a one-to-one relationship between these two. So if you use the joint PDF, it gives the distribution. The characteristic function also gives you the distribution. It fully characterizes the distribution of your random variable, your pair of random variables. Another important definition is that some people, they take logarithm of that. They look at this one in a log scale. It has some interesting properties. You remember that in your signal and systems, if you have, let's say, x of t convolution with, let's say, h of t in Fourier domain, you have x of, let's say, omega multiplied by h of omega. So the convolution, which is a complex operation, becomes multiplication, which is easy to understand, to calculate and manipulate. Now, if you take logarithm in frequency domain, then the result, let's say this is y of t, this will become y of omega. So ln of y of omega becomes ln of x of omega plus ln of h of omega. So in a log scale, the convolution becomes addition, which is easier to understand. So similarly, this property, which convolution is converted to addition in the log domain, also is exploited in statistic. And for this reason, we define the second joint characteristic function. And this definition is nothing more than logarithm of this function, or logarithm of this double integral, and is logarithm of this moment.